Let me welcome you to the 6th lecture of our course in reinforcement learning. Today, we're going to talk about two subjects, model predictive control and multi-agent problems and rollout algorithms for them. Okay, here's the outline. First, we talk about model predictive control, a major methodology in control system design, and also of particular interest to us because it involves a lot of the elements of reinforcement learning. And in fact, it has a lot of commonality with the AlphaZero architecture and the TD-Gammon architecture that was the starting point for our course. We're going to talk about issues of stability, which are very important in control theory, and also discuss a few variations of the basic algorithm. Then we're going to talk about multi-agent problems involving a control that consists of multiple components corresponding to different agents. We are going to discuss them in general, and then we are going to develop a rollout strategy for these problems that is economical from a computational point of view, discuss policy improvement issues around that. Then we are going to discuss the case where the agents have some autonomy and they may be on their own, not fully sharing their information, and we'll see what happens under these conditions. Then we are going to discuss an application. I'm going to show you a demo, not a demo, a video. It's not very sophisticated, but I think it conveys a lot of intuition. It involves a multi-agent problem and a challenging POM-DP situation, partial state observation, Markovian decision problem. And actually, I have two videos, and the one that's going to be longer is this last one. So we're going to go into model predictive control now. And in this lecture, I'm going to use clips, video clips from last year's lecture. And I'm going to go now to the clip. Its principal area of applications is in control system design, and in particular, its problems that involve infinite control spaces, where some of the ideas that we discussed in connection with deterministic rollout do not apply, because the number of Q factors is infinite here at any one state. And there are two major types of problems in control system design. One is called the regulation problem, where you want to keep the state of the system near some given point. Traditionally, this point is taken to be the origin, 0 of a Euclidean space. If it's some other point, then we can make a translation of the coordinates so that that point of interest becomes the origin in the new coordinate system. So, for example, this inverted pendulum problem, a classical problem that is a good test bed for algorithms, but also is intuitive. And it relates to keeping this pole that has a mass at the end of it, keeping it upright, which corresponds to this angular velocity being 0, and I'm sorry, the angular position being 0, and the angular velocity being 0. That's the place where we want to keep this pole. And we want to do this by applying control horizontally on this car. We move the car so that this mass gets to the upright position and stays there. So this is a regulation problem. And another major problem involves following a given trajectory, controlling the system close to some given trajectory. Like, for example, we have this car here, and we have a trajectory that we want it to follow that goes from point A to point B. And we want to do this with minimum cost, but also observing various constraints. In automated car designs, there are a lot of constraints that you have to observe. For example, there are control constraints like there are velocity constraints, how fast or how slow the car can go, acceleration constraints, and this play also with the state constraints. And the state constraints may be staying on the road, avoid some fixed obstacles, and also avoid moving obstacles like other cars that may be crossing into your path. And so we have to worry about things like going too fast into a turn, and we have to reduce velocity before we go into the turn. Similarly, we have to worry about cars crossing into our path, and we have to do online replanning, just get around of those moving obstacles. Now, when these constraints are critical, they are safety constraints, and you can't deal them in a soft manner, deal with them in an indirect way. You have to deal with them directly. Unfortunately, the linear quadratic formulation, a classical control formulation that we have discussed in this course, is often inadequate in this context because it does not deal directly with state and control constraints. It deals with them indirectly by using these quadratic penalties that may be violated in the formulation of the problem. This is not acceptable in situations like this. And this has given rise to the methodologies that fully respect the state and control constraints, and model predictive control is one of these methodologies, a principal one. Okay, so now we're going to deal, there are many different formulations of the model predictive control problem, and we're going to call it MPC, abbreviate MPC. It's a popular acronym. So there are many different types of MPC formulations, but the one that we're going to deal with is the original one, which dates back to the late 80s. We have a system that's deterministic, state XK, control UK, and this can be linear or non-linear, but it has an origin, an absorbing state. 0 is a state that once you go into, you stay there, okay? That's what this means. No matter what control you apply, once you reach the origin, you stay there. Of course, this is an idealization that would not be true if the problem was stochastic and there was some noise here, but we consider in this formulation a deterministic problem as an approximation. Excuse me. Okay, so now the cost structure of this problem encodes our desire to go to the origin with minimum cost. So there has to be an incentive for driving the system to the origin. And this is encoded by positivity of the cost, except at the origin where there is no cost. The origin is cost-free. No matter what control we apply, once we are at the origin, we stay at the origin at no cost. And we have control constraints. We don't have any state constraints. There are extensions of this formulation that involve state constraints, and I'm going to discuss them a little later, but for simplicity, we are going to keep state constraints out of this formulation. We also assume perfect state information. The control is applied with full knowledge of the state. In practice, when this may not be satisfied, but what people often do is to use estimates of the state as if they were exact. So in other words, there may be an estimator that tries to figure out where the state is and then forms an estimate based on observations, which are used then by the controller as if, by the MPC controller, as if they were exact. There are also other formulations involving imperfect state information, but this is a common one. It's easy to explain. Okay, so this is the problem. And what does MPC do? Well, at a state xk, it solves an L-step look-ahead version of the problem and requires that the terminal state is exactly 0 while satisfying the constraints. In other words, at xk, it looks ahead L steps and tries to bring the state exactly at 0, minimizing the intervening cost. And of course, once the state is at 0, it stays at 0. So then, assuming that it can solve this problem, of course, the original problem may have much longer horizon, may have an infinite horizon. So this problem is easier, okay? It has shorter horizon. And there are ways to address problems like that, particularly since it is deterministic and the self-step problem is deterministic. We assume that this can be done, okay? Now, assume that at xk you have solved this L-step problem. You have obtained a control sequence, an optimal control sequence for this problem. And then you apply at xk the first component of the solution and you discard all the rest. It's like rollout, where at some state you apply a heuristic and you obtain a trajectory. And then you keep the first step of the trajectory and you discard the rest. And indeed, there's a close connection between MPC and rollout, which I'm going to discuss now. Okay, so what does rollout do? It minimizes over Q factors, and these Q factors involve minimization over the first stage, over the control, the Q factor at xk and uk. It calculates this Q factor and then applies a base heuristic for the remainder. So this looks pretty much like what we have in MPC. And in fact, you can see that MPC is rollout with a base heuristic being an L-1 minimization to 0, okay? Not L-step minimization. The base heuristic is the L-1 minimization that is at the tail end of this figure. So this is first step minimization, and then base heuristic and L-1 stages minimization. And we can fold the first stage with the remaining L-1 stages into a single minimization to obtain an L-step minimization, which is exactly what MPC does. So MPC does this L-step minimization, but the base heuristic starts from the state xk plus 1. And let's call h of x the optimal cost of the base heuristic starting from x. So we are at some state x, we do this L-1 step minimization, and the cost of this minimization is denoted by h of x. Similar to the notation that we have been using for rollout, for base heuristics. Now, it turns out that this heuristic is sequentially improving. Okay, we talked about sequential improvement and sequential consistency also. It turns out that this heuristic is sequentially improving. It is not sequentially consistent. And I can explain this briefly, but we're not going to insist too much about that. It's not sequentially consistent because if I start here and apply this base heuristic and then move to the next state here, the base heuristic from this next state is going to take you one step forward. So it's not going to be the same trajectory as the one that the base heuristic generated from this state. So it's not sequentially consistent, but it turns out that it's sequentially improving. And the definition, of course, of sequential improvement is this inequality here. The minimal Q factor at x is less than the cost of the base heuristic. The minimal heuristic Q factor, going one step and applying the heuristic from the next state. And this holds trivially, okay? It's very simple to see why this holds. Why? Because the right-hand side is the optimal cost from x to 0 in L minus 1 steps, okay, from X to 0 in L minus 1 steps, and then stay at 0 for the additional steps. Now, the left-hand side involves the first step minimization and then L minus 1 step minimization, and then stay at 0 for the remaining steps. So this optimal cost to reach 0 in L steps is less than the optimal cost to reach 0 in L minus 1 steps, because the solution of this problem is a feasible solution for the solution of this problem, a feasible solution for this problem, and the optimal solution for this problem is better than the feasible solution. So we have this very simply. And now, once we have this base heuristic being sequentially consistent, being sequentially improving, a lot of nice things follow, including cost improvement. The cost of the rollout policy is less than the cost of the heuristic applied from the same initial condition. And this translates to this inequality here. This is the cost of the rollout, okay, for a given initial condition here. Let's consider the state and control sequence generated by MPC, okay, and the rollout algorithm that underlies MPC, starting from X0. Then sequential improvement implies that over n steps, this cost is going to be less than the cost of the base heuristic L minus 1 minimization starting from X0. And this is finite. So as you go forward and you generate more and more controls and states, this sum remains bounded. And because the cost is positive, unless you are at 0, the only way this can stay bounded is if you approach, either reach 0 exactly or approach it at a fast enough rate. Control engineers define this as stability, okay? Bringing the system to 0, the reference point, regulate it there at small cost. Bring it and keeping it there, That's the notion of stability, which for control engineers is paramount. Control engineers don't care nearly as much for optimal cost or low cost as they care about stability. If your system is not stable, forget it. We're not going to even look at it. So that was the main selling point of MPC. It's not just that it reduces cost through rollout, but it generates a stable controller. And people have been playing around with different versions of MPC, trying, for the most part, to keep this stability property intact. Okay, are there any questions so far on MPC and how it relates to rollout?
I have a question. So you don't necessarily know if you're at state xk that you will be able to reach state 0 within L steps, right?
Right. So you don't know that.
Okay.
So you're right. It's a good question. Yeah, go ahead.
What I was thinking is the idea just to try to make as much progress towards state 0 as possible. But if you happen to reach state 0 before the L steps are up, then you just stay there. Is that the idea?
No.
Okay.
This constraint that you reach the reach 0 in L steps is a hard constraint. It's part of the method. Okay. Now I'm going to get into a variant of MPC which does not have this requirement, but in this formulation of MPC, it is a requirement that you reach the origin in L steps. And if L is not enough, you just increase it, okay? And there's a certain, this is an assumption here in our context. However, in control theory, there's a concept of controllability, being able to reach from any one state, any other state in a certain number of steps. And the number of steps for n-dimensional system is typically n. Otherwise, we don't have controllability. So implicitly here, we assume controllability, that you can get from any state into the origin in L steps. And L must be large enough to be able to do that.
Okay, and then
So I'm glad you brought it up. Yeah, go ahead.
L doesn't need to be constant from iteration to iteration, right?
Well, in this slide, it has to be constant. It is constant, at least for the base heuristic. Now, okay, for this slide, it's supposed to be constant. In variance of the method, it may not be constant.
Okay, so there's just an assumption that you will always be able to reach 0 within L steps.
Exactly. This is an assumption here, and I'm glad you brought it up. Yeah.
Okay, thank you.
Okay, guys, I'm going to switch back to slides now. And this is a good time to ask some questions on what has on the lecture so far.
Yes, I have a question.
Yes.
So, like, you're assuming controllability, but is there any assumption on like the dynamics can be generally nonlinear?
Notions of controllability become much more difficult if the dynamics are nonlinear. Usually controllability is easy to deal with for linear systems. There's also an additional difficulty here that if there are state constraints, if there are control constraints, then there may be some states that you may not be able to reach from the origin because your control, the available control is not enough. Basically, it cannot do it for you. So all of these questions need to be looked at in greater detail, but certainly if the system is nonlinear, then these questions become more difficult. Okay, so now we were going to discuss a major variation of MPC, where instead of requiring at the end of L steps to reach the origin exactly, we impose instead a terminal penalty for missing the state, the origin. So this becomes L step minimization without a terminal state, without the constraint that at the end of L steps we hit the origin, but instead there's a terminal cost that is positive for X different than 0 and 0 if you do hit the origin. So the solution is of this problem is similar to the solution in the previous slide. And the control constraints are the same. The system equation, again, deterministic. Everything is the same except for substituting this constraint with a terminal penalty. Now, once you do that, then we are in familiar territory. This is just approximation in value space with L step look ahead with terminal cost function G. So this is the kind of scheme that we have been studying so far without any rollout, but just L step look ahead minimization. Now, we want to discuss the stability of this scheme and more generally how it behaves. And there's a certain condition that we will see that it guarantees stability. This condition is on G. Not every G works and gives you a stable policy. However, we are going to show that if G satisfies this condition here, okay, you have to interpret this condition as follows. T is the min-Bellman operator of the problem. You remember from a couple of lectures back, the min-Bellman operator and the mu-Bellman operator and the abstract framework that we use to interpret various methods, including one-step and multi-step look ahead. So this condition translates to this for all X. And this expression encodes the T operator acting on G. It's a function of X. So G is a function of X and TGs of X is another function of X. and we require this condition. And you may notice also that this condition looks quite familiar, and in fact pretty close to the sequential improvement condition that we've been dealing with rollout. Now, we can show that this condition here implies stability of the MPC controller that solves this problem at every step and uses the first control of the optimal sequence at that state. Your textbook has an analytical proof of this, but what I'll do in this lecture is give you a graphical argument that's far more intuitive. It's not quite, you can be made rigorous, but the way I'm going to present is not rigorous, but it's far more intuitive. And this argument involves the graphs of the Bellman operators, and also it involves the concept of the region of stability. Okay. In one step look ahead with cost function approximation J tilde, we say that J tilde belongs to the region of stability if the policy obtained by one step look ahead minimization is stable. And a stable policy is one that has a cost function that's finite for every state. The cost function doesn't blow up. All of these concepts, region of stability and the like, make sense basically for the case where that MPC applies, non-negative cost and zero at the origin. So that's how we define the region of stability, and we can visualize it as follows. Okay, so this figure should be familiar from a couple of lectures ago, and it involves the graph of the min Bellman operator, the T operator. It's a function of J, the cost approximation. We are showing it here in one dimension so that to be able to visualize it. But it is monotonically increasing, it is concave, and its fixed point. The fixed point of T is the optimal cost function. The Bellman equation is J star equals to Tj star. And J star is obtained at the intersection of the graph of Tj and J. And in addition to the min Bellman operator, we have the mu Bellman operators corresponding to various policies. Now, the mu Bellman operators are linear. They have linear graphs, and they are like so. And we have shown that the min Bellman operator, the red curve, is the lower envelope of these mu Bellman operators. In other words, if you draw all of those and take what lies below, you're going to obtain the hypograph of this T operator. And we have interpreted now one step look ahead with cost function approximation sum J tilde as follows. We go up here and we find the tangent policy, the policy that comes the lowest towards approaching the point T sub J tilde. And that is the one step look, the graph of the one step look ahead policy. So for different cost function approximations, we obtain various one step look ahead policies. And some of these policies are going to be stable and some of them are going to be unstable. Now, in this figure, you can see that the ones that are stable are the ones that correspond to cost function approximations that are to the right of this threshold point. And this threshold point corresponds to the slope here being equal to 1. If all the tangent policies that correspond to points to the right of this have slope less than 1 because of the concavity of the red curve, and all the policies that correspond to all the tangent policies that correspond to points to the left of this threshold point are unstable. they do not intersect the 45-degree line. They have infinite cost, at least for some initial states. So this is the region of stability. And if we pick G within this region, then we are going to obtain a stable MPC policy. Now let's look at the condition TG less or equal to G. What are these G's? They are the ones that lie to the right of J star, okay? Because that's the threshold point where the curve goes below the 45-degree line. So the region where TG is less than G, and more generally, TJ is less than J, is this region here. It is a subset of the region of stability. However, if you pick G within this region, then what is the one-step look-ahead minimization policy? We go up here, we find the tangent policy, and the cost function of that policy is bounded above by G. And given that G is finite for all X, the same is true for the one-step look-ahead policy, so it is stable. All of these points here satisfy G less or equal, greater or equal to TG, and also give you stable one-step look-ahead policies. Now, even if you do multi-step look-ahead, and instead you construct TG and then T squared G and so on, you're still going to be within this region of within this region here, always lying above J star. So even if you do multi-step look ahead, starting with a G that is within this region, you're going to obtain a stable policy. So that's the interpretation of this condition here. In control theory, it is often called a Lyapunov condition. We have called it also sequential improvement. Basically, it relates to this figure as you see here. Are there any questions on this figure? Okay, so let's work on this figure in a little bit more detail and how it relates to stability. Now we're going to look here at an abstract visualization of MPC with L-step look-ahead minimization and a terminal cost function G satisfying this condition. Okay, this picture is a little complicated. Perhaps you'll get out of it without understanding all the fine details. However, it is important to study this figure and the one in the next slide because it will tell you more. It will give you more intuition than reams and reams of equations and analysis. So that's my advice. What I'm going to try to do here is go slowly through this figure and please ask questions if there's something that's unclear. So we have a terminal cost approximation at the end of L-step look-ahead minimization. And we assume that this terminal cost approximation G satisfies this condition. Now, how do we visualize MPC? Okay, so we have again the min-Bellman operator, the red curve. It has this fixed point, which is the optimal cost function of the problem. The region of stability starts to the left of J star and corresponds to this point where the slope is equal to 1. The region where this condition is satisfied starts to the right of J star. And now let's consider MPC with three-step look ahead. So three-step look ahead minimization and terminal cost function G. How would that work? We go to G, construct T's of G, and then T squares of G, and then we're ready to do the first minimization. That first minimization will give us a tangent policy, and that tangent policy is precisely the MPC policy. and it has cost function J tilde mu that is smaller than G, which is assumed to be finite. So the MPC policy is stable. Okay, let me go through this once again. Start with G. One step look ahead, second step look ahead. The third step look ahead will bring us horizontal to this point. But the third step, which is the first step in of minimization, finds this tangent policy, which intersects the 45-degree line at this point and gives you this cost. This is the cost of the MPC policy. And the very last, or perhaps the first, depending on whether you look at it from the beginning or the end, the very last minimization is the Newton step. The rest is preparation for the Newton step adjustment of the starting point. So this condition guarantees stability of MPC, of the MPC controller with L-step look-ahead minimization. Are there any questions here? I urge you to understand, try to understand this figure. I think you'll gain a lot from it, much more than you can get from analysis based on equations and things like that. Okay, now I'm going to take you one step further. If you thought that the previous figure was complicated, this is even more complicated. It deals with MPC with L-step look-ahead minimization and M-step truncated rollout before reaching the terminal cost function approximation. So here's a diagram. At a state X, we do L-step look-ahead minimization, operating on the results of M-step truncated rollout with terminal cost approximation G. And the truncated rollout is done with a stable policy, mu. So the operation is abstractly denoted like so, T mu, M steps of that, operating on the terminal cost approximation. And the results of that, which is this thing here, we apply TL, L steps of look-ahead minimization to it. And the very first policy that's obtained from this minimization is precisely the MPC policy with L-step look-ahead minimization and M-step truncated rollout. Now, this figure here involves an extension, and the extension is the M-step truncated rollout. If we didn't have this M-step truncated rollout, it would be exactly the same as the figure of the preceding slide. However, now we have a one-to-one mapping to the AlphaZero architecture. And moreover, this type of MPC is very well known and widely practiced in control system design. In fact, it is the method that you get when you use the MPC software at MATLAB. This is what you get the options to set LM and the policy and so on. And basically, the MPC people have been doing about the same thing as the reinforcement learning people have been doing with chess and backgammon and the AlphaZero type of architecture. It's really the same thing. It's a matter of emphasis, different emphasis. Most of the emphasis in reinforcement learning type of applications goes into the training, the offline training. The MPC people have been looking far more on the issues of look-ahead minimization, how you implement this look-ahead minimization, and also how do you guarantee that the MPC controller is stable. Otherwise, the methodologies are very, very similar, and one has to gain a lot from cross-fertilization of ideas from the other. Okay, so now I'm going to try to explain this figure here in terms of the Bellman operators. Are there any questions as to what we're dealing with here? Excuse me. Okay, so here's the min Bellman
Professor,
operator.
Sorry, I have a question.
Yes.
I was a little bit late. Like when you say like truncated rollout is what in MPC, it's basically the like it's an horizon where the control is fixed,
Yes.
but we still like simulate the system for that horizon.
That's right. Yeah.
Okay, thank you.
Yeah. There is something called the control horizon, which is this, and the prediction horizon, which is this entire thing. Okay. And this part of the horizon involves a fixed stable policy. So you crank the state policy with terminal cost function approximation G, and this is fed as terminal cost approximation to the control horizon. This is, of course, a much more difficult minimization than this part, okay? That's the good thing about rollout. It is a much cheaper substitute for look ahead, looks forward with less cost because we use a single policy as opposed to minimization. Okay, so let me go now into this figure. We want to translate into this figure this block diagram, and we want to construct whatever comes out as a final cost approximation to the L step look ahead. So how is this done? We start with G and we apply value iterations with the stable policy mu. This is the base policy, okay? It has a linear mu Bellman operator, and the cost function of mu is this point here. I don't show it, but this is what it is. It's at the intersection of this line with the 45-degree line. And let's take a G here, which incidentally is not in the region of stability. However, we apply truncated rollout to it, and then we push it towards the region of stability. This point here certainly is within the region of stability. And with the value iterations, we move towards the region of stability. And then we do M here is equal to 4. 1 step takes us here. 2 steps take us here. 3 steps take us here. 4 steps takes us here. This point is T mu to the 4th power on G. And now this is what's being fed as the terminal cost approximation to the L step look ahead minimization. And now the L step look ahead minimization does value iterations. L equals 2 here. So it does 1 value iteration, and then it does the initial value iteration, which finds the tangent policy and the MPC policy. So in this figure, the cost function of the MPC policy is obtained through this journey, starting from G, roll out 4 times, going here, then coming down here, and then look ahead minimization twice, once, and then obtaining the MPC policy. And the last step is a Newton step. The remainder is determining the starting point of the Newton step. And now the nice thing about it is that it's clear that by doing rollout with a stable policy, we improve the stability properties of the system. We push the starting point of the Newton step, we push the effective approximation at the end of the M step look ahead into the stability region. And then whether we do 1 step look ahead or L step look ahead, it doesn't matter. Once we are in this region, then we get a stable MPC policy. So larger values of M and also L, if you look at variations of these figures, make the MPC policy stable. Large values of M push the starting point of the Newton step towards the cost of the stable policy. Large values of L push the starting point of the Newton step towards J star, okay? I know it's a little confusing, but if you study this figure, you'll learn much more than you would by looking at analysis that take pages and pages and complicated equations.
Professor, I have another question. Like here, J star, like the optimal cost is for an infinite horizon problem, or and that we try to solve with MPC with the L step look ahead, or like what is it, the optimal cost J star in this case?
The problem that we're considering here is infinite horizon.
Okay.
In other words, it's the sum of all the costs over an infinite horizon. Now in MPC, we look at L steps look ahead, and we have to assume that J star is finite. Okay, this is part of the assumption, but this can be guaranteed as follows. If we can bring the initial state to 0, then we can keep it at 0 for all the remaining steps. So the infinite horizon cost of that kind of control sequence that brings you to 0 is finite, okay? The main assumption here is that from a given initial state, you can bring the state after L steps to 0. And then after that, over an infinite horizon, there is no additional cost. So this figure is for an infinite horizon problem with positive cost per stage, okay? A lot of this analysis here is predicated upon a positive cost per stage as it is in the case of MPC. Whereas there are figures like that for finite horizon versions of the problem, they are more complicated, and we're not going to look at them for the time being. Any other questions? Okay, so we look at one variation of MPC involving terminal cost function approximation with and without truncated rollout. It's very closely connected to approximation in value space. It maps directly onto the AlphaZero architecture, and it is quite standard in MPC. So now we have omitted a few things here, and MPC is a very broad subject. It has been researched for now 35 years or so. There are many variations. We have focused on deterministic problems, and we have omitted something significant, which is state constraints. We have not addressed state constraints at all. In practice, state constraints can be very important. In fact, if there were no problems with no significant problems that involve state constraints, there would be no MPC. The reason for existence and prominence of MPC is precisely because it can deal with state constraints in ways that a linear quadratic formulation cannot deal. So we have not, we have sort of assumed away this part of the problem, and it actually, it imposes significant difficulties. Here's the difficulty. Suppose you have an unstable system. Okay, you look at the system, you see this 2 here. It's unstable. If left uncontrolled, it takes off, okay? By a factor of, the state increases by a factor of 2 at every step. Now, of course, you can use control to bring the state down, but suppose that you have control constraints. Your control is limited to be between 1 and -1. Then if the state goes off significantly away from 0, then you can't bring it back. You just don't have enough control. So suppose that we have a state constraint of this type, that the state of the system has to be kept within a cube. A cube is a sequence of sets that constrain the states, the successive states of the problem. If A is greater than 1, then if we start close to A, or certainly above A, the state of the system cannot be kept within the constraint. We're going to take off to infinity. On the other hand, if A is less than 1, then we can keep the state of the system within the cube, no matter where we start within the cube. Okay. So that's an important property. We need to have cubes that when we start within them, we can keep the state of the system within them. And the initial constraint may not be such a cube. So that's what we need to construct offline, an inner cube from within which the state constraints can be met. In other words, if you start within them, you stay within them. You can stay within them. And this leads to methods of reachability of target cubes. Cubes with this property are called reachable cubes. And it's a subject dear to my heart because it was a significant part of my PhD thesis long time ago. You can find all this, my thesis online, was the first to deal with this issue of reachability. And the ideas found application much later within the context of MPC. For like 15 years, nobody ever looked at my thesis. All of this is explained in much greater detail in the textbooks for this course and also in the videos from the two previous offerings of this course from 2019 and 2021. There's a lot of discussion about reachability and how it plays an important role in model predictive control. But in this version of the course, I'm not going to discuss it any further. There are other variations. We talked about terminal cost function approximation and doing truncated rollout with a base policy. How do we get those? Well, it's possible to get them by training with data, using neural networks or using some other kind of approximation methods to construct them. And this ties in with the second part of the course that and the training methods that we're going to start discussing in a couple of lectures. We have assumed that the problem is deterministic. However, there are versions of MPC formulations that involve uncertainty, both stochastic uncertainty and also minimax worst case uncertainty. Now, the difficulty with this type of MPC is that the L-step look-ahead minimization problem is stochastic. It's a stochastic dynamic programming problem with L-step horizon. And to solve it online, it may be difficult. There are ways to deal with that to some extent. For example, simplification of the minimization. And a major form of simplification is certainty equivalence approximations, whereby we replace the stochastic quantities with deterministic ones, and we solve the corresponding deterministic problem, which is much simpler to solve than this stochastic L-step problem. It's important, however, to keep stochastic uncertainty for the first stage in order to take advantage of the power of the Newton step. It's only if you have for the first step stochastic uncertainty that you maintain the Newton step interpretation. So this is something I talked about in the last lecture, and you may want to look at it some more. Okay, are there any questions here? We're done with the with MPC. We're going to go into multi-agent rollout now. And I'm going to switch to a video from, again, last year.
Multi-agent problems, I talked about them briefly in lecture 3. And as I said, it's a very old field, goes back to the 60s. And in fact, my PhD work, I spent 6 months working on this field and got discouraged because it was so difficult, at least in the time, for those times. But the field has gathered a lot of steam, a lot of popularity with the advent of reinforcement learning. It refers to multiple decision-making entities, which we call agents. Now, each agent has a control that it applies. Agent 1 applies decision U1, 2 applies U2, and so on. The overall control is the collection of these decisions. And the agents apply these decisions by using information. The information is obtained from other agents or from the environment. So it's a sequential decision process. At time 0, agent 1 applies a control U1. All the agents I apply decision UI. Some information exchange takes place. A new state is generated. Then there is a decision-making around again. Information exchange, new state, and so on. So we're looking at a sequential decision-making framework, applying decisions by this collection of agents in discrete time based on the information that is received between applying these decisions. And now this is a complicated problem that involves many applications, but it's very important to keep in mind the major mathematical distinction between different structures of this type. The first one is the classical information pattern. I mentioned this in lecture 3. In the classical information pattern, the agents are fully cooperative, they fully share information, and they never forget information. So they're really part of a team, a collaborative team, and they share all the information. Now, if this is the case, then we can view the collective decisions of the agents as a single decision, essentially, applied by a single super agent, if you'd like. And with that view, we can apply dynamic programming. Okay. So that's the main consequence of assuming this classical information pattern. It can be treated by dynamic programming, therefore bringing into play the algorithms that we have been discussing and the full methodology of dynamic programming. A far more difficult case, relatively speaking, is when you have a non-classical information pattern where the agents do not fully share information. They have some private information, and they may also be antagonistic, like in a game type of problem, either zero-sum game or a Nash type of game. Now, when you have a problem with this type of information pattern, it immediately becomes very hard because it cannot be treated by dynamic programming. Not only are approximations essential, but you have to be, they're very difficult to solve. In our course, we're going to stick with dynamic programming. We're going to assume a classical information pattern, but at critical points, we're going to venture into the non-classical information pattern case through various generalizations. But the starting point is a classical information pattern, whereby the agents have exact state information, they share all the information that they need, and they choose their controls as functions of the state. So conceptually, you can view this structure as involving some kind of a information collecting cloud, an information clearinghouse, so to speak. Collects information from the agents, collects information from the environment through various sensors, condenses this information in all the information that the agents need, and passes it on to the agents in the form of state information. So the state, the exact value of the state that I'm talking about here, is given by the cloud, which collects all this information. That's a conceptual view. And of course, it may be unrealistic in a given problem, but it's a good starting point to understand the classical information pattern structure. Okay, so now our model is going to be a stochastic dynamic programming model that we know and love from our early lectures, finite or infinite horizon, with state denoted by x, xk for time k, control uk at time k. And the only way in which multi-agent problems differ from what we have been discussing so far is that the decision has this component structure. U, the control, involves M components, which correspond to M agents. Now, the term agents may be a little misleading. Agents is just a metaphor. The important structure is just components, M components. And these components may correspond to agents that are geographically distributed within a certain area, or the components may reside on the same computer, okay? They may control different arms of the same robot that based on computations that are done inside the robot. So agents is just something to gain intuition from, but it is not, the only characteristic is this multi-component structure. And this type of structure involves a lot of difficulty with computations, lots and lots of computation, because the search space, because of the multiple agents, may be enormous. So what we're going to set as our initial goal is to apply approximate dynamic programming and rollout ideas aiming at faster computation in order to deal with the exponential size of the search space, the control space. Even if these U's take two values apiece, the search space becomes 2 to the m, the size of the search space. And pretty quickly, it can get enormous. So we want to deal with that problem in various computations involving rollout, approximation, value space, and so on. And there's a second idea here. We want to allow these agents to have some autonomy, to be able to apply their controls simultaneously. Now, of course, there's a bit of a conflict here because they have to exchange information before they apply their controls. But we're going to try to deal with this difficulty. And in the process, we will deal in part with issues that stem from a non-classical information pattern. Non-classical information patterns very much arise in systems where agents are autonomous and they don't quite have time to share their information. But we view this problem, this issue, from the point of view of speeding up the computation through parallelism, parallelize the decisions of the agent controls. Okay, so now we are going to apply rollout to this multi-agent problem setting. And the only thing that we are going to assume that's different is that U has this component structure. And what I'm going to talk about applies in finite horizon problems as well as infinite horizons problems. To simplify the notation, we're going to consider infinite horizon problem. And notice that the standard rollout operation in its exact form is this. What do we do here? We do at state X, we do approximation in value space by minimizing the approximate Q factor of a base policy mu. In other words, we use one step look ahead with cost function approximation that is given by the cost function of this base policy mu. Now, because this is a base policy, sequential consistency holds, which is important for the analysis. However, when we look at this operation, we see that it's a major problem in the multi-agent setting. The search space, the minimization, grows exponentially with M. So there may be just too many Q factors here to compute, and this is a difficulty. What comes to mind is simplified rollout, where instead we simplify this minimization. And one form of simplified rollout is this multi-agent rollout methodology that I'm going to discuss now. Remember that simplified rollout under sequential consistency implies cost improvement. So I'm going to claim cost improvement at the end of the day. Now, how does this simplified rollout work? Well, instead of doing minimization over the joint decisions of all the agents taken together, we do minimization one agent at a time with intermediate communication of the controls chosen between the agents. So we are at state X. We want to simplify this operation. What do? Well, we have a base policy and we minimize over the controls of the first agent, okay? So this is minimization not over the combined vector of agent controls, but just over a single agent control. And how about the controls of the other agents? Well, we use for the subsequent agents, we use the base policy controls. Given X, we can compute the base policy controls for agents 2 up to M, and we can set up this minimization with respect to the control of the first agent. Now, this may be a vastly simpler minimization than this. It has potentially a much smaller search space. So we do this minimization and we obtain mu tilde 1 of X. This is the rollout control of the first agent. And then we go to the second agent. We communicate to that second agent the rollout control that agent 1 has chosen, and we do a minimization over the control of the second agent only, with the previous agent's control chosen already by rollout and the future agent controls chosen by the base policy. So that minimizes, this gives you the rollout control of the second agent. Then we go to the third agent, the fourth agent, and so on, up to the very last agent, where we have already computed the rollout controls of agents 1 up to M-1, and we minimize over the control of the last agent. So starting from X, we have computed the rollout control by means of this one agent at a time minimization process. Now let's count the Q factors that this process involves. This is exponentially in M. However, the number of Q factors is linear now in M, assuming a fixed number of controls for each agent, a search space that involves, like, say, 2 controls or a finite number of controls. Then the number of Q factors goes linearly with M. M times single agent minimization. And that's a truly enormous speed up. But the other nice thing here is that this is simplified rollout with sequential consistency holding. As a result, we have cost improvement, which is sort of a good property to have. I'm going to explain this cost improvement in a different way also, but I think it's useful to keep in mind one avenue through which it is implied, which is the fact that we're doing simplified rollout here. Okay, now your class notes do not talk about multi-agent problems very much, but there's a long survey paper that I have published recently. It's about 70 pages or so. And it has a lot of material, both on multi-agent rollout and also multi-agent policy iteration, a subject that we're going to talk about later in this course. And the paper can be found from our website. And this is a survey paper, but the earlier papers from the last 2 years that are coded there with various variations of multi-agent rollout, various theoretical analysis, and so on. There's also a computational paper with multi-agent rollout, which I'm going to discuss later in this lecture. Okay, so are there any questions on what we do in multi-agent rollout in this one agent at a time process? Okay, so let me
just pause the video here and ask for questions. Do you have some questions about multi-agent rollout? Okay, we'll keep going with this example, the spiders and flies example.
Illustrate multi-agent rollout in the context of this spiders and flies example. I think I mentioned this example in lecture 3 as well. We have a grid, and there are 15 spiders somewhere within this grid, and they can move in the 4 directions, up, down, right, left, or they can stay where they are. And the objective is to catch a number of flies in minimum time. And these flies are at various places in the grid, and they move randomly, and they're totally blind. On the other hand, the spiders have perfect vision. They can see where the flies are exactly, even though each time they change position, of course, they can update the location. They can track visually the flies. And moreover, they can see where the other spiders are. So at least they can visually coordinate, so to speak. So now we have a multi-agent problem, right? Because they have 15 agents, the 15 spiders, and each one has 5 possible moves. So the number of joint move choices is 5 to the 15, okay? An astronomical number. Now, multi-agent rollout will reduce this to 5 times 15, which is just 75 Q factors, as opposed to that many Q factors, while maintaining cost improvement. And it works by applying a sequence of 1 spider at a time moves. So the way it works, we have an order 1 to 15 on these 15 spiders. And the first spider selects its move by doing a rollout minimization, assuming that the other spiders use a base heuristic. And the base heuristic that they choose, we are going to assume here, some kind of a shortest path heuristic. Each spider moves to the nearest fly directly along the shortest path. So there is a base heuristic, a shortest path type of heuristic, and spider number 1 assumes that the other spiders are going to follow this base heuristic. It's going to select one of the 5 possible choices. communicates this choice to spider number 2, which does the same, taking into account what spider number 1 has done and using the shortest path moves that for the other spiders. And then spider number 2 chooses one of the 5 moves, communicates, broadcasts this move to all the other spiders, and then spider number 3 moves, 4, 5, all of them go in turn. Each time there's 5 choices, and the total is 5 times 15 for 75 choices. Now, here the spiders make their moves sequentially. So that slows down the process. In other words, spider number 2 cannot make any decision before it hears from spider number 1, and so on. These choices are serial in nature, and they are important because they imply coordination. Basically, spider number 1 tells spider number 2, I'm going to go to this one. You better go somewhere else because I'm going to catch this one within the proper amount of time. On the other hand, we're going to try to introduce a limited form of coordination by using signaling information, like some imprecise information that coordinates the moves between the different spiders. And we hope to gain some speed up because of the simultaneous choices of the spiders. And the speed up is going to be up to 15, okay? So for the moment, we're going to assume that we have full communication of the spider moves to other spiders, and later we're going to come back to this. Okay, so I have a video illustration of this process. And before I go into that, are there any questions about this problem?
Did someone ask a question?
Yes, Professor, I was asking if that is going to be the classical type, like every spider will know the other spider's decisions and the conditions.
Yes, the video is going to be of that type. Every spider observes where every other spider and knows where every other spider is, and knows the location of the flies. And also there is this assumption of one action at a time, one spider at a time, whereby each spider learns the moves of the predecessor spiders in the order, and assumes that there will be the choices of the following spiders in the order is going to be done according to the base policy. Okay, so this is the video that I'm going to show you, and I'm starting it now.
Okay, so let me go into the video. Now I'm going to show 3 possibilities. 2 spiders and 2 flies using spiders use the base policy, shortest path, the standard form of rollout, and the multi-agent form of rollout. And the base policy is going to be to move along the shortest path to the closest surviving fly. And I'm going to use the Manhattan distance metric for calculating shortest paths. And this base policy uses no coordination. All the spiders act, the 4 spiders act as if they were by themselves. There was no other spider by themselves. So now let me see if I'll manage to show you this video, because I'm not very experienced. I'm digitally challenged, I should tell you that, but you probably have figured it out already. So now I'm going to show this one here, the base policy. Okay, so Okay. So we have 4 spiders, and for this example, they are located right in the middle. And there are 2 flies that move at random, okay? And these 4 spiders try to catch the spider, the spiders try to catch the flies in minimum time. So what would be the reasonable thing to do? Well, the reasonable thing to do would be to split off the spiders, and 2 of them go one way, 2 go the other way. And also, since there are 2 of them and the flies move randomly, it may make sense to sort of try to encircle the spider. So if randomly it goes away from one of the spiders, it can be caught by the other spider. Okay, on the other hand, this base heuristic, the shortest path, is selfish, no coordination, and let's see how it works. Okay, so now we see that the spiders do not split off. They go towards the closest fly. Okay, in the Manhattan distance, the spiders break ties by moving along the horizontal or are moving along the vertical. 2 of them prefer the horizontal and the vertical. So now, with no coordination, they have all done the same thing, caught this fly, and then they rush off to the other surviving fly along the shortest distance based on the Manhattan metric and the preference that they have between horizontal and vertical. Now, this guy here moves back and forth, up and down, and so on, but eventually the spiders are going to get him. Okay, there's no way it can escape. So I'm going to advance the video a little bit. Okay, so now, okay, they got him. Okay. So that's not very smart, okay? And it took 85 time units to capture both flies. So let's see now what the standard rollout will do, okay? This is not multi-agent, this is standard. So this minimizes over 625 Q factors at each move. It's going to take 34 moves. At each one of these 34 time units, it's going to minimize over 625 Q factors. Moreover, these Q factors involve a stochastic system because the flies move randomly, so it will involve Monte Carlo simulation. So it's quite a bit of computation to compare 625 Q factors. But we're going to show the results here and see what kind of policy you get. You expect it to be smarter, right? The rollout is supposed to be smarter than the base heuristic, given particularly that we have cost improvement. So let's see what we get. Here's what happens. Oops, sorry. Okay. So they both start at the same place. And what you're going to see is that they do something more intelligent. 2 of them go that way and 2 of them go that way. They split off because they coordinate with each other through this joint move selection. Okay, 2 of them are going towards this one and 2 of them are going towards this one. They have perfect vision, but the flies move randomly now, right? And you see that they try also to do something that's a bit intelligent in that they try to, okay, still this has not been caught yet. This one has started going in the other direction, okay? Having caught this one, then it realized a good idea to go and try and catch this one. But of course, it's unnecessary because these 2 are perfectly capable of catching this eventually. The expected time to catch is very small. So that's what the standard rollout will do. And now let's see what the the multi-agent rollout will do. Now, this involves a lot more computation, only 20 Q factors for each time step, and gives you the same capture time. It performs just as well. So let's see how this works. Again, the behavior is indistinguishable between multi-agent and standard rollout. Again, we have split off between the spiders towards the two different flies, and there's some attempt towards they get close to a particular fly. And the capture time is the same as for standard rollout. Okay, so are there any questions about this demo? I realize that it's kind of primitive, okay? But, okay, I haven't done many movies or that in my presentations. I haven't used them in my presentations so far. So I'm still a novice, and it's a little primitive. However, I have heard from one of you who is interested in doing a project, a term project involving spiders and flies, but a much fancier problem formulation involving a better video, among others. So hopefully, in next year's offering of the class, I'm going to have a better video to show. But for the moment, that's all you get. Okay. Have any questions?
I have a question. So what would this look like in like a non-classical setting if the agents were being antagonistic? Would it be somehow like a competition to capture all the flies, or is that what you sort of meant by that? Antagonistic agents?
Okay. This problem does not lend itself to an antagonistic setting. I mean, what would be antagonizing here? The only way you can have a zero-sum game out of this is when you have attackers and defenders. So some spiders are attacking the flies, and some spiders defend the flies, okay?
That makes sense.
The analogy doesn't hold up very well.
Okay.
So, however, it's a legitimate question on what do you do if you have both, you have multiple agents, some of which form a vector of minimizing a cost function that minimize a cost function, and some of which form another vector that maximize the cost function. So that would be a legitimate problem. It's an open question. It's an open research question of how multi-agent rollout would apply to this setting. It has not been done. So if some of you want to look at this, that would be an interesting subject to explore either analytically or computationally.
Okay.
Any other questions? Okay, I'm not done with demos, and the next demo is a little better. I'm sorry, I used the word demo, and I meant video. Demo is something that's supposed to be much more highbrow. So let me go back to full screen. Okay, so now let's take a break. Take a break for like 15 minutes. And I want you to, if you wish, to think about how we might approach this multi-agent setting and multi-agent rollout analytically. And I gave this figure in lecture number 3, and I explained it very quickly, But now I want to go into it a little bit more in depth. This involves a reformulation of the problem whereby each transition from state xk to xk plus 1 is split off, is unfolded into multiple transitions. The first transition involves choosing the first control component by agent number 1. Without cost, we move to this state here, then choose a control, the control chosen by agent number 2. It leads to this state, and so on. So we choose controls one agent at a time, and the last control involves the system equation, okay, to state xk plus 1. Up to here, we have xk and the first m minus 1 components. Having chosen the mth component, we are ready to move into state xk plus 1 according to this equation, because this uk involves all the components. And this last transition involves also the cost of the xk to xk plus 1 transition with a discount factor here. The preceding transitions involve no cost. Now, I want you to think why this problem formulation involving a different state space and a breakdown of the transitions in this way, why this is equivalent to the problem that I have been discussing. And I want you to think about applying standard rollout, not multi-agent, standard rollout to this reformulated problem, which involves choices of one component at a time. And also think about cost improvement, how it comes into play in the context of this standard rollout. So think about all this, the transition from standard rollout to multi-agent rollout, this reformulation, which involves a more complicated state space, but a simpler control space. And we're going to take this break for 15 minutes and come back at 6 o'clock, let's say.
Okay, guys, we're taking a break for 15 minutes, and we'll get back. Think of this question if you wish, and we'll discuss it after we come back. There was a question in the chat about the homework. The homework has to do with spiders and flies, a problem of that kind. The question was whether you're supposed to do videos of your results. No, you're not supposed to do videos. You can just report the results in any way you prefer, and you can use any software that you want to do your calculations. Are there any questions about the homework along that line? Okay, there's some comments in the chat. Naturally, you're welcome to do videos and present the results in whatever way you wish. Actually, we could use better videos than the one that I have presented, use them in the future. So if you want to go into more sophistication, you're most welcome. And also, if you want to do a project relating to more sophisticated versions, more elaborate versions of this type of multi-agent problem, as the spiders and flies, you're welcome to do that. It's I think it's a fruitful area where you can learn something from. Let's get started, and let me go to.
Any comments about this formulation? Why is it equivalent? And how does it relate to how does it connect standard rollout with multi-agent rollout?
So it's using state space augmentation. For every state in the multi-agent rollout problem, you're sort of replacing it with every possible sequence from 1 to m-1, but also from 1 to m-2 of these possible decisions. So, for example, the number of sequences for m-1 agents is going to be the size of the largest control set to the power m-1, but then you also have to add all the ones for m-2, m-3, and so on down to 1. So you have this sort of enormous explosion in the size of the state space when you are converting it to a standard rollout problem.
Yeah. Yeah, the two problems are equivalent. In other words, the one where the transition is just straight from xk to xk plus 1 using a control that's a joint control over all the agents, okay? And the one that we're breaking down the decisions into multiple decisions. The policies for this problem, the reformulated problem, can be represented also as policies of the original problem. You take a policy here that's a function of the current state. Let's say this one is a function of the state xk and uk1. uk1 is given by some policy, so altogether u2 is also given by a policy. So you're not gaining any new policies in the reformulated problem. And for every policy of the reformulated problem, there's a corresponding one of the standard problem with the same cost function. Therefore, the two problems are equivalent from the point of view of optimal policies and optimal cost. But as Jameson mentioned, there is the state space grows enormously in this reformulated problem, whereas the control space is simplified enormously at the same time. So we're trading off control and state complexity. It's an old idea, by the way. And what's happening here is that if you were to solve this problem exactly, you would have to deal with cost functions that relate to these parts of the state space, additional cost functions in addition to j's of x. However, when it comes to rollout, that doesn't bother us because rollout does not look at the size of the state space at all. All it looks is just the current state and it looks to apply control out of the one control out of the admissible controls. And having to do that in stages makes things simpler for rollout. Moreover, if you look at the structure of multi-agent rollout, it's just the same thing as standard rollout for the reformulated problem. And whereas, as I said, the size of the state space does not adversely affect the application of rollout. So we gain from this, we gain the cost improvement property. The multi-agent rollout is standard rollout for the reformulated problem. Therefore, it improves the cost function of the reformulated problem, which is the same as the original problem. So that's one other way to verify the cost improvement property for multi-agent rollout. There are three different ways. One is through simplified rollout analysis. The other one is what I just mentioned here. And the third one, which is analytical. You'll find all this in this survey paper that I mentioned earlier. And of course, the main benefit here is that the one-step look-ahead branching factor is reduced from n to the m to n times m, where n is the number of possible choice for each component. Okay, so let's go now into a special case, multi-agent MPC, okay? MPC is like rollout. So what does, how can MPC benefit by applying multi-agent rollout? Well, there's one case that I can think of, perhaps there are others. Suppose that that you have MPC where the control consists of both discrete and continuous components. So it has a continuous component, which I call V, and it has some discrete components, like integer variables. Now, we motivated MPC based on problems with continuous control space, but we made no assumptions about the structure of the control space. MPC, the analysis I gave you, the stability analysis, applies to discrete control spaces, continuous control spaces, or mixtures like here. And this kind of situation can be useful in a number of settings. For example, this Y's may be system configuration variables. Values of YKI being 1 or 0 may correspond to different parts of the system being configured in the position 1 or 0. Like, for example, in a power system problem, where you want to address economic power generation. This YKIs may correspond to the ith unit, the ith generating unit being online or offline, being on or off. And in power systems, very often, in fact, as a matter of course, you have generating units turn on when there is period of high demand and turn off when it's period of low demand. So turning a unit on and off is part of the optimization. And then there are also continuous variables, how much electricity to generate from the power plants. And okay, so this is an example where this situation may occur. Now, if you try to apply plain vanilla MPC with a control space like that, you have a serious problem, because the MPC problem, the MPC minimization over L steps, becomes an integer programming problem with a potentially large number of integer variables. These Y's complicate the solution a lot. And therefore, it would be nice if you could treat these Y's one at a time, as you would in a multi-agent type of rollout. So how would you apply that kind of rollout in this setting? You need a base policy, which may consist of a nominal configuration that depends on the state. So the base policy gives you for each state a set of discrete components and a continuous component, a continuous control policy. And in a component by component, a multi-agent version of MPC at state xk, we first choose the discrete variables one at a time, an easy optimization problem with all future components fixed at the values determined by the nominal configuration. And then after you have chosen this Y values, choose the continuous component to drive the state to 0 in L steps with minimum cost, with the discrete components fixed at the values that you have calculated earlier. So this simplifies a great deal the MPC problem and separates the difficult minimization over the Y variables from the continuous minimization over VK. And these minimizations can be approached with different methodology, like the continuous minimization may be approached with nonlinear programming, whereas the integer minimization may be approached with combinatorial integer type of integer programming type of methods. So that's the, in a nutshell, the idea here, making the look-ahead minimization simpler by separating the components and treating them one at a time, and the stability property and the cost improvement property of MPC is maintained because multi-agent rollout has a cost improvement property, and it's also a simplified form of rollout, a simplified form of MPC. So are there any questions here? Okay, let me go into the question of autonomy. We want the agents to act more or less independently and not wait for each other to apply their controls in sequence. On the other hand, the multi-agent rollout operation is inherently serial. So how can we parallelize it? First, to get extra speed up, and also be able to introduce some agent autonomy into the process. Okay, so what's the obstacle to parallelization? To compute the agent L rollout control, we need the rollout controls of the preceding agents, right? This is how multi-agent rollout works. We choose the rollout controls of the agents one at a time, and we pass on the values to the future agents, to the next agents. So the reason we have to wait and do things serially is because of this need to communicate, of early agents communicate their controls to subsequent agents in the order. Now, the idea here to remedy this is to use pre-computation. Pre-compute the rollout controls and use guesses, these mu hats in place of the preceding rollout controls. Do some pre-computation and figure out what are the rollout controls, roughly, that the multi-agent rollout algorithm would apply at state X, and give them to the agents so they don't have to wait to hear from the other agents in applying their own controls. They use these mu hats in place of the mu tildes. Now, this opens a great deal of, a great number of possibilities. One possibility that comes immediately to mind is for the agents to use, instead of the rollout controls of the preceding agents, use the base policy controls. In other words, use as mu hat the base policy mu for each agent. But I'm going to argue that this may not work well, may be quite unreliable, because essentially that throws away all kinds of coordination between the agents. Another possibility is to do some pre-computation and train a neural network to emulate approximately the rollout policy controls and use the output of the neural network and thereby obviating the need for serial computation. The agents do not wait to hear from other agents. They simply use the neural network output, which has been trained offline. And there are also other possibilities that are problem specific. Now, I'm going to show you what will happen. First, what will happen if you use this approach, which is the simplest, right? You don't have to do any pre-computation. You use base policy controls in place of rollout controls in a multi-agent setting. And here's an example. Using the base policy for signaling. And what's the pitfall with that? Here we have two spiders and two flies, and they're on the line. And the spiders try to catch the flies in minimum time, and the flies are stationary. They're not moving randomly as they were moving in the grid example. The spiders have perfect vision, perfect information, and the flies do not move. And let's consider a base policy whereby each spider moves one step towards the closest surviving fly. So let's say that this is the state. The two spiders are in these locations, and okay, so spider one looks at the two flies and says, which one is closer to me? That's fly number two. So it moves one step towards that. Spider number two does the same thing, looks at this fly number one, fly number two, and moves again to its closest one. And they don't make any attempt to coordinate. And that's the base policy. So given a state, we look at the closest flies and we move the spiders one step towards them. On the other hand, this is not optimal, right? Because, for example, for this state here, the base policy would move both spiders towards this fly. This spider is going to arrive first, and at that point, they both reverse course and go towards the fly number one, right? They move one step towards the closest surviving fly. On the other hand, the optimal thing to do is clearly to split the spiders and have one go in one towards one fly and the other one go to the other fly. So the split has to be done so that this one does not go to this and this one goes to that. They split towards their closest flies. That's clearly the optimal policy. It catches the flies in minimum time. Is this clear? Are you guys following? What's happening? Are there any questions?
I think it's pretty clear.
Yeah,
Okay, I'm glad to hear that. Ask questions even if it is clear, okay? Because I just get to speak to myself only, and that's not very good. Okay, so that's pretty easy to see that the optimal solution is to go towards the closest flies. Now, something that's not obvious is that if you apply the standard rollout, not multi-agent, but just the standard rollout where the spiders jointly choose their moves, it turns out that the standard rollout is optimal for all the initial states. No matter where you start, it will be optimal. Of course, this connects to the cost improvement property of rollout, but it's nice to see that it actually works optimally for all the initial states. And okay, so I'm going to go through this very quickly, but I'm going to ask you to do this as an optional homework to verify that this is indeed true. Okay, the standard rollout. Okay, I'm going to do this. It turns out that the agent by agent, the multi-agent rollout is also optimal for all initial states. And this can also be verified. And let me sketch the proof of that. Let's say spider number one selects a move first, and then spider number two will select. Then spider number one looks at the two Q factors, going here, and then going here, and going here, and then going again here, because the base heuristic is go towards the closest fly. Now, it assumes also that it contemplates these two Q factors, and it assumes that spider number two and subsequent choices of spider number one are going to be based on the base heuristic, go towards the nearest fly. So if we go and choose this move, this Q factor, we're going to end up closer to this fly, but fly number two is going to end up catching that fly first. So this move was wasted. On the other hand, this move here is going to gain a leg up. We're going to be, once spider number two catches fly number two, we're going to be one step closer to catching fly number one. And if you compare this Q factor and this Q factor, this one will win. As a result, spider number one is going to move, or is going to choose this move, and then it's pretty easy to see that spider number two is going to choose that move. So with this implicit coordination, trying to take into account what the other spider is going to do based on using the base policy allows us to differentiate between the two Q factors and choose the optimal one. So that's roughly the idea, but I want you to verify that. It's going to be a good exercise of whether you understand the definitions, if you can figure it out, if you can figure out that these two statements are indeed true. Okay, so this is agent by agent rollout, taking into account the rollout control of the preceding policies. Now, suppose that we use signaling using the base policy. Then there is no coordination between the spiders. And it actually turns out that rollout with this base policy signaling works optimally for most of the initial states. But there's a significant exception. Suppose that the spiders start at the same location, one on top of the other. Then if they have no coordination, they're going to move towards their closest, the rollout algorithm with this signaling policy is not going to be able to differentiate between the two directions. And if one chooses in one direction, the other one will also choose in the other direction. So they will always move in unison, and they will be oscillating and never catch the flies. In particular, if both of them start in this location, rollout with base policy for signaling is going to move in the wrong direction. It's going to take us all the way to the left, up to the point where we reach the middle. And at that point, we reverse course and then go back and forth like that. You can, if you wish to try to write a little software program to test this, this behavior, that would be a good exercise if you prefer that from analysis, but you can see this from analysis as well. So let me not discuss this point further. I leave this to you as an exercise to verify it, but I'm going to show you a similar phenomenon in the video that I'm going to go into now. Are there any questions? Okay, so this is the recent paper that I did with 4 of my ASU colleagues, Shmita Bhattacharya, Siva Kailas, Sehil Bayal, who by the way is our grader for this course, Professor Stephanie Gill, who has moved now to Harvard. And there's a paper that we wrote a few months ago, and you can find a copy from my website, and it deals with multi-robot repair of a network of damaged sites. Okay, so we have here a network of sites. Think of a pipeline here, a pipeline network. In some parts, in these locations, there are several locations in this network that may be damaged, may have sustained some damage, and there are 5 different levels of damage, and they're illustrated here by this symbols. So this corresponds to damage level 0, which is like this site is not damaged. Level 1, like this one, slightly damaged. Level 2, a little more damaged. Level 3, even more damaged. And that's the worst kind of damage, okay? Now there's a cost to be paid for leaving an unrepaired site, for leaving a site unrepaired. And a big complication here is the fact that we don't know the damage level of each site. We can only find out about it if we actually, the robot goes there and inspects the location, in which case it finds out the level of damage. Moreover, the damage level changes over time. It deteriorates according to a known Markov chain. So from slightly damaged can go to more damaged and even more damaged and so on over time. So what we have here is a POM-DP. a partial state, partial observation Markovian decision problem, where the exact state is not known, but we receive observations about that state. And what are these observations? They are these inspections. When the robots go to the different sites, they observe the condition of the site and they ascertain which level of damage it has sustained. So here, the state is the set of robot locations. Here we have 4 robots, okay? There are 4 of them, and they can be anywhere in the pipeline, and they move 1 step per time unit, 1 step at a time. And the state of the system is a set of robot locations and the conditions of the damage level of the sites. And each one can have 5 different levels. So the number of states is astronomical. Even if you had perfect state information, the number of states would be astronomical. Moreover, here you have partial state information, which means that the state of the system is actually the belief state over the state, the set of probability distributions over the site damages, plus, of course, the set of robot locations. So we have a POMDP. The belief state evolves according to a known process because we assume that there's a Markov chain here that's known, how the damage levels progress probabilistically. And the control choice of each robot is to, given that it is at a certain location, either inspect and if it's damaged to repair, or to inspect and move to a neighboring site. However, repairing takes 1 time unit, which is time that you may need to go and visit a more damaged location. So the trade-off here is fixing damages early, spreading out the robots more or less evenly within this pipeline, and also take care of urgent damages at the highest level, which cost more per unit time. You want to rush robots towards this most damaged locations so that they don't cost you as much. So that in a nutshell is the problem. It's a very, very challenging problem. And we have addressed it with rollout, but unless you use multi-agent rollout, the problem becomes extremely difficult because there are just too many Q factors here, and this Q factor to calculate costs you because you need Monte Carlo simulation. Here we have shown, I'm showing 4 agents, but the number of agents may be larger, maybe 10, 15, 20, already very high numbers. But in other versions of this problem, in other settings, the number of agents may be in the hundreds, okay? So any thought of standard rollout is out of the question. And multi-agent rollout becomes the only hope that I know of, at least if you want to apply an approximation in value space type of method. So that's the problem. And I'm going to show you some videos of solution to give you an idea of how this multi-agent rollout works with possibly signaling or without signaling. Are there any questions? Is the problem formulation clear? We have a POMDP with an already very complicated but discrete state. And however, the POMDP involves a belief state. That's the one that we are operating on. And this is a continuous state, space of probability distributions. We have multiple agents, and we have we have a system equation that involves the belief state, and Q factors are calculated by Monte Carlo simulation using the known Markov chain.
One question, are all agents aware of the same most up-to-date belief state?
Yes. Yeah, we assume that that the inspection results go up to some computational cloud that calculates the belief state and passes it on to the agents.
Okay, understood.
And now, in our formulation so far, we have considered damages that are uncorrelated with respect to location. In other words, the damage is this location is uncorrelated with damage in neighboring locations. This simplifies the problem because the belief state becomes a Cartesian product of probability distributions corresponding to the different sites. This is called a decentralized POM-DP or DEC POM-DP in the literature of POM-DP problems. The more complicated problem is when there are correlations between the probability distributions of the different sites, and then there's no way to pass on the probability distribution to the agents because it's a very complicated object. And that would therefore necessitate that the computational cloud uses some kind of neural network to represent the belief state and passes on the neural network output to the agents. Of course, that's a more complicated version of the problem, and I don't know how it would work out, but it's one step in. It's the next step, one of the next steps from what we have done so far. Okay, so now I'm going to show you three videos, three of those four. One is the base policy, where all the agents, all the robots, they go to the nearest site. Each one goes to its own nearest site that has some damage. In other words, has a probability distribution that that indicates that some damage is possible. And that's the decision it makes. And also the base policy, if it finds a site that has damage, it fixes it. It doesn't skip it to go to a more urgent, to go and address a more urgent repair. So the base policy is pretty naive, okay? It's shortest path, greedy, and so on. And then the other video has to do with multi-agent rollout, where the robots, they choose, they make moves, they make choices serially, one after the other. So robot number one chooses what it wants to do and then sends the information to robot number 2, 3, and 4, okay? So this is the multi-agent rollout algorithm. Now, this algorithm here is multi-agent, but trying to cut corners, introduce signaling, and in particular, the base policy signaling, like in this 2 spiders and 2 flies example that I gave earlier. Now, we're going to see some pretty bad stuff from this one. And we also have another video where the signaling has been calculated with a pre-trained policy network. And I'm not sure that I can show you that, but here are the results, okay? The base policy cost, and this is a discounted problem. We formulated it as a discounted infinite horizon problem. The base policy cost is calculated to be 52.94. Takes 30 steps to fix all the damages, assuming that once you fix a damage, it doesn't become, the site does not become damaged again. So fixes are sort of permanent. Multi-agent rollout takes a lot less, 9 steps. This one with base policy signaling works pretty bad, okay? And I'll show you why. And with signaling based on a pre-computed neural network policy is in between these two. It tries to emulate this, but it does so approximately, only approximately. Therefore, it loses some performance, which is reflected both in cost and in number of steps to terminate. Now, I'm going to discuss rollout here, but I will return to this problem in the future in the context of policy iteration, infinite horizon policy iteration, a multi-agent type of policy iteration. So now let's see, I have to show you the videos. I'm going to show you this one first. Okay, just one moment. Okay, the base policy. Okay, this is a higher quality video than the one I had before. And I have deliberately started all the robots in the same location. Now, this base policy, the shortest path or greedy policy, has no coordination. And what you expect it to do is the robots ignore what the other robots are doing. They all go to the closest damaged site. And because they start at the same location, they will all be doing the same thing, the exact same thing. So let's see if that happens. They start here and they all go to the same place. One of them fixes the site while the others have to wait. Notice that new damages pop up, become worse. But this one has perfect vision about which sites are damaged, somewhat damaged, and it moves accordingly. And now it's finished. And here's the cost, accumulated cost in this 30 stages. Okay, so the base policy has no coordination. Let's look at the multi-agent rollout without signaling. Okay, so now all of them start at the same location, but they tell each other what they're doing. So we expect to see the robots splitting up and say, like robot number one says, well, I'm going to go this way, you go some other way. And this guy's, and then all this information is passed around and they intelligently divide their tasks among themselves and spread out throughout the pipeline. So there you see, some of them go one way, some of them, they split off, and pretty quickly, after 9 stages, they have cleaned up the pipeline, and the cost is much lower. Okay. So now I'm going to show you oops, that's not the one I want. Okay, so this is multi-agent rollout with base policy signaling. In other words, the agents don't wait to hear from the other agents, but instead assume that they will be using the base policy. Okay, Now, this is like the bad case of the 2 spiders and 2 flies example. Let's see what happens. They just can't make up their mind. And they go back and forth. Okay, they never accomplish anything. And the cost will stay finite because this is a discounted problem, okay? Well, discounted problems have finite costs. But it's clearly very bad, and so obviously this policy is doing some very, very bad things. What's the reason that it goes back and forth like this? Well, let's take the first one agent. The agent considers its Q factors, the Q factor of going here and the Q factor of going here. Now, okay, so this is agent number 1 that's considering these 2 Q factors. And it has to figure out what agent number 2 is going to do. Now, it assumes that agent number 2 is going to use the base policy. So agent number 2 is going to go here, the closest damage. So agent number 1 says that this agent is going to fix this damage, so I shouldn't be going this way. I should be going that way. And that's why it decides to make this move. Now, agent number 2 is going to think exactly the same way. And it also is going to move to this side because it thinks that this one is going to go that way. And similarly, all of them have groupthink. They all think that somebody else is going to do something different than what they're actually doing. And they move back and forth like this. So that's the danger of using signaling with the base policy that it's just neglecting any kind of coordination between the agents. Okay, are there any questions about what's happening here? What's the confusion? What the difficulties are with this this policy? Okay, so let me show you the last one, which is which tries to emulate by using a neural network. It tries to emulate this multi-agent rollout policy. Okay, I'm going to go quickly through that. It's going to do similar things, but less perfectly. Again, you can see that the agents split up. They have split up, and but they're doing it less intelligently, with less efficiency, because the neural network is not passing correct information, entirely correct information. So as a result, you have that with neural network signaling, we get something, we get performance that's in between these two. Okay, so this was my last slide, or next to last. I have one more slide about what we're going to do next time. Are there any questions? Here's your last opportunity to ask questions.
I have one.
Yeah.
What kind of data is used to train that neural network in the last example?
Yeah, okay. Well, we want to obtain a policy network that emulates the rollout policy. So we simply run the rollout policy, obtain training data from the rollout policy. In other words, at different states, we obtain data as to what the rollout policy, the exact rollout policy, will do, the multi-agent rollout policy. Mm. And then we train the neural network on that data. It's going to construct a policy that's going to be sort of similar to the rollout policy, but not exactly the same because the training is imperfect, okay?
So the data is based on multiple runs of the multi-agent rollout policy, or the multi-agent rollout example.
Yes, and this is all done offline.
Offline.
You do a lot of computation offline in order to be able to do faster computation online, in order to avoid to have ready-made, pre-computed coordination, basically.
Okay, that makes sense.
Okay.
Excuse me, Professor. I have a question.
Yeah.
I just want to know, is it possible to solve this problem with the, rollout itself, the one that all agents decide at once?
Yes, yes, but it's very time consuming. But it's possible in principle to solve it.
Okay. And then we should expect it to have better results, or at least the same result as multi-agent rollout, right?
The theory does not tell you whether one form of rollout is better than the other. The standard rollout or the multi-agent versions. There is no clear superiority of one over the other. What's going to happen in an individual, in a particular case like this problem, is not very clear. We haven't tried it because the standard rollout is too time consuming, okay? A lot more Q factors to calculate. Basically, it requires 4. Each agent has a number of degrees of freedom, right? And also fixed or not fixed. So it's something like 4 to some power, okay? That depends on the branching factor here. So with 10 agents, it becomes overwhelming. With 4 agents, perhaps we could have done it, okay? But we just haven't done it. So in principle, there is no clear superiority, analytically speaking, there's no clear superiority of multi-agent rollout versus the standard rollout. In practice, however, the two, at least for this type of problem and for the spiders and flies type of problem, they're pretty much the same, okay? There's no intuition that would favor one type of algorithm over the other. That's all I can say for the moment. And we're doing other experiments at the moment, and we hope to have more insight into this question going forward.
Okay, thank you.
Any other questions?
I have a question about a neural network. So,
Yeah.
So because your policy is changing with time, so when you generate a new policy, the network will also change, right?
Well, for a given problem in a given base policy, we assume that the base policy is sort of fixed.
Okay.
If we change the base policy, of course, the rollout policy is going to change and the neural network will have to change. But ordinarily, the base policy does not change, okay? And here, if you try to make the base policy more complicated, you're going to have difficulty.
So the neural network.
Go ahead.
So the neural network is just to use to fit the base policy.
The rollout policy, not the base policy.
Oh, the rollout.
The base policy is sort of something simple, like a shortest path type of go to the nearest damage site type of policy. It's the rollout policy that's hard to calculate because it requires a lot of computations, and we pre-compute an approximation to that using a policy network.
Okay.
Okay.
So guys, I'm stopping the video, going back to my last slide. So are there any questions? Okay, we had a lot of questions, but from the previous class of last year, are there any questions that you have about the video that I showed?
So I had a quick question, but it's a slightly question regarding a slightly more general case. So in the most general version of decentralized POMDP, each agent is meant to act based only on their observations, right? So there need not be any mechanism for the agents to communicate what actions they select. In those cases, would multi-agent rollout not be possible?
Okay, that's not a problem of classical information pattern.
Okay. Okay.
Yeah, because the agents do not share the same information.
Yeah.
Here we assume that the belief state is calculated by some cloud,
right,
and it's passed on to the agents, but this belief is simplified, has a decentralized structure, has a decomposable structure.
Right.
One side uncorrelated with the belief state of each side is uncorrelated with the belief state of the other sides.
So I was just, I thought it was interesting because you had mentioned decentralized POMDP in the video. And also, if each of the agent had some access to some kind of signaling based on neural network, it would still be helpful there, even though they don't have access to the other agents. So I just thought it was interesting. So this one to mention.
Yeah, there are many possibilities that suggest themselves in contexts like this, and there's such great variety of problems. I mentioned that we're doing more work and so on, and indeed, with the same team of Professor Gill's students, slightly different, we're working on other problems that have similar flavor. For example, a taxi dispatching type of problem, like an Uber routing type of problem. And there, the number of agents is enormous, okay, because there are a number of taxis in the road network. And however, there's a different structure of observations, different belief state structure, and so on. There are other types of problems involving firefighting, for example, where the agents are the firefighters or teams of firefighters. And there you may have observations of the fire location and spread from overhead observers, and you may have even exact state information at each time, okay? So you may not have to rely as much on the observation of the agents. So, okay, there are many different cases. Each case may be slightly different, but it makes enormous difference. Even slight differences in the problem formulation make enormous difference in the methodology that's suitable for that problem.
Thank you. Yeah, that was my question.
Okay, so in the next lecture, we're going to close our discussion on rollout algorithm by considering constrained deterministic problems. Problems where there are constraints not only on the actions, on the controls available at each state, but also on the entire trajectory of the system. And there are applications of this type in combinatorial and discrete optimization. We're going to cover those, and we're going to do a variety of other material, closing out our discussion of rollout algorithms and preparing the ground for getting into neural network approximation and training 2 lectures from now. Some sources for today's and the next and next week's lectures. The draft of my book, Lessons from AlphaZero, has more material on both rollout and MPC. I gave this survey paper reference earlier from my website, and there's also a video in my website, the same website that contains all the class material, which those of you that are interested in multi-agent stuff may watch. It has it's more extensive than what I gave in this lecture. About homework. There is homework solutions as part of the class notes for the first 2 homework. The third homework is exercise 1.3. And it's our last homework, and it's due, okay, February 27th. It's a couple of weeks from now. It's time for you to look into options for your project, other term paper of the read and report type, or a mini research project. Whatever your thinking is, don't hesitate to send me email, and I'll provide suggestions and advice as to whether this might be suitable. And depending on our communication by email, we can make an appointment to talk by Zoom, and either one-on-one or myself with a team of you, whatever is appropriate. So that's all for today. Are there any questions on this agenda that we have? Okay, so I'm going to now unshare my screen, and see you next week.